So yeah, it's my great pleasure to welcome Xingyu Zhu, who's a neighbor in Detroit, in Wayne State. He's an assistant professor there in the EC department. He received his PhD from Ohio State University. We shouldn't give too much negative association. That being said, his research interests include machine learning, so he's going to talk about that, privacy and robustness, stochastic systems, applied probability in general, load balancing, for example. He's particularly interested in decision-making with formal privacy or robustness categories. I mean, his work's been published in all the top conferences like NeurIPS, including AAAI, ICML, Sigmetrics, AI Stats, and he's also received the NSF Career Award. He's been a TPC for many top conferences as well. In fact, he's going to be helping out with this ACM Sigmetrics next year, which is going to be held in Ann Arbor. Shameless plug for that. The other thing that he's famous for, and with that, is there's a blog that he has, which is on strong convexity, which is apparently extremely popular. Anyway, with that, I'll give the floor to Xingyu.
Yeah, thanks for Regis' introduction and the invitation. It's my great honor to speak here to talk about my recent work on privacy and robustness. It will cover some of my recent work on Bing estimation, bandits, and also large language model alignment. Okay, so yeah, so let's jump to the topic. Mean estimation. So maybe I would claim that is one of the most fundamental statistical tasks in machine learning, right? So the goal is very simple. You are given a target distributions and you are going to estimate the mean, right? And since we are doing machine learning, we are given a bunch of samples. Ideally, they are sampled ID from the distributions. And our goal here is basically to design an estimator such that the distance between your estimator and the true mean should be close, right? And suppose the distribution is nice, for example, the distribution is bounded, and a simple application of this Hopefully lemma will give you this kind of 1 over root n convergence rate, right? So this is very low. Of course, if the distribution is not that nice, then you cannot use the empirical mean, right? In reality, your samples may not be ideal in the sense that they are ID sample from your target distributions, right? They are maybe sample from a lot of distributions. And this can come, or this can happen because several factors. The first factor could be privacy issues, right? So we want to protect the data privacy. What does it mean? For example, each data point, you can even think about this xi as a bit, right? And in many cases, this bit is sensitive, right? In the sense that I will give you a concrete example, right? So during the election period, which one do you select, right? So this kind of information, I definitely believe it is somehow sensitive. You do not want others to know your preference, right? So how can you do? What can you protect? What can you do to protect your privacy, right? In this sense, I think, for this binary data is quite straightforward, right? You can just do some kind of random flipping, right? So instead of report your true preference, X, you just convert to something like Y, right? The Y is basically a randomized version of your true bit in a certain sense, right? So for example, if you want to guarantee some formal privacy guarantee in terms of the DP terminology, this is called the local differential privacy, which is formally defined as this, right? It says that no matter which input it is, the probability of observing the same outcome should be similar. In other words, an adversary observes your output cannot distinguish whether your input is X or X prime, right? So in that sense, it will give you the formal privacy guarantee in the DP language. And this epsilon characterizes the closeness or this this kind of privacy protection strings, right? Okay, so for this kind of binary data, it's quite simple to design a privatizer to guarantee epsilon LDP. This is maybe the most famous LDP mechanism, which is called randomized response, right? Very simple. With some probability slightly larger than 1/2, you keep the truth, otherwise you flip. And you take the ratio of the two, that will give you the e to the power of epsilon, which will guarantee epsilon LDP, right? Cool. Just random flipping. Okay, so in practice, there is also often another case that your data or samples are not that ideal. This could be from corruption, right? So, okay, you report your privatized feedback a bit, but during this kind of data collection process, there could be some kind of adversary corruption, right? So in this sense, the learner can only observe the Z rather than Y, right? So in this talk, we will focus on this particular corruption model, which is commonly used in the robust statistic literature, which is called a Huber corruption. It basically is a probabilities mixture. It says that with probability alpha, this true data will be sampled from, or your outcome will be sampled from some bad distribution. Otherwise, it will keep sample from the good distribution, the inlier distributions. Okay, the bad distributions can be arbitrarily chosen. It can even depend on the good distribution and even can depend on your algorithms.
But it cannot depend on the sample.
Cool. Yeah. If it can depend on the samples, then that we call the strong contamination model, and we will discuss that model in the end of this talk. Okay, cool. Yeah, I'm waiting for that question actually. Okay, so okay. So
there has to be some regularity assumptions in this.
No. Yeah. Okay.
I mean, like if you're measuring for a mean and it doesn't have a mean, what's
Yeah, it's okay. But there is something I will talk about that. Okay, cool. So you can see we call this particular interplay between privacy and corruption as the LTC. I would admit this is definitely not a good name, but the LTC stands for LDP then corruption. Basically means LDP happens before the corruption. Okay, so L stands for LDP. Okay. Okay, so this is a first situation that you first do the privatizer and then you have the corruption. I think this is very natural, right? This is not something artificial scenario we come up with. This could happen in practice, right? Yeah. So another situation is so-called corruption then LDP. So the data source itself is already corrupted, right? So think about like this, right? Some adversary can control some sources such as the inner bits or the good bits have already been corrupted, right? The privatizer is unaware of such kind of corruption. So in this sense, we call this setting like a corruption then LDP like set here. Okay, so the order of the privacy and the corruption changes. That's the only difference. Okay. So basically, we have introduced these two settings, LTC and CTL, for this interplay between privacy and robustness against corruption. And I would argue that these two settings are somewhat universal in the sense that beyond the mean estimation, right, you can apply this modeling idea to many other situations, like, you know, in the learning literature. For example, some online, offline bandits, reinforced learning, large language model, and many more. So as long as you have some kind of feedback and the feedback is sensitive and could be corrupted, then you can use this kind of, you can study these two settings, right? It's a meaningful setting. Of course, you may wonder, okay, the corruption can also happen before and after this kind of privatizer, right? This is also reasonable in practice. And it turns out that this setting is not that interesting at all because even though it is very generic, but it turns out that if you have a good understanding of LTC and CTL, the statistical rate for this kind of most theoretical scenario is just a plus. So it's not that interesting. Okay. So in other words, as long as we have a good understanding of these two basic models, we will have an understanding of that model. In the literature, robustness has a very broad coverage, right? In this talk, we mainly focus on the adversary robust against adversary corruption, but the robustness can also mean, the Hilbert distribution, like inlier distribution X could be sampled from Hilbert distributions, right? Some of the results can be easily generalized to the Hilbert distribution, and we will talk about some of them. But I want to highlight is that this kind of privacy, corruption, and Hilbert distributions are actually closely related to each other in some very fundamental and principal way. That means that if you have one algorithm which was originally designed for, say, privacy, it can be utilized to design an optimal algorithm for Hilbert mean estimation. It can also be used to design an optimal algorithm for mean estimation on the corruption. So vice versa. So they are very fundamental. Okay. So now you may wonder, there is a ongoing large body of work on this interplay. What's your difference? So the minor difference here is that in this line of work, they mainly focus on the central model differential privacy, which means that the learner has access to the raw data. But in this talk, we mainly focus on the local model of differential privacy, where the user has already privatized the data. So the learner, the central learner, only has access to the privatized version of the data. Okay, cool.
When you say corruption, do you mean the individual user itself is corrupted?
Oh, that's basically in the CTL setting, you can think about like each individual data has already been corrupted before it goes to the privatizer. But in the LTC, the corruption basically happens during the data collection process.
Is it like a hardware failure or?
Oh, it could be, right? It could, yeah. We consider Hoover corruption model. That can be used to model maybe hardware failure or maybe even VC specification, those kind of things. Yeah. Okay, so by corruption, I mean something like this. Sorry, by corruption, I mean something like this. Your observer data is some mixture of the good data and the bad data, a bad distribution. Okay. So as a very direct application of the mean estimation, we can apply it to the online multi-embedded. I believe for the audience in this room, you are definitely familiar with this setting. So it's just learning multiple means on the fly, right? So suppose you have multiple advertisements, you want to, for each of them, it has this kind of mean, which is the click-through rate, right? So how likely this advertisement will be clicked by the users. And we want to identify the best option. So what we can do here is that the learning agent try to run this kind of MAB learning protocol. At each run, choose an action. Action here basically is the add option and observe the sample, right? So basically in run T, it samples from one, interacting with one user and gives the feedback from that corresponding action. And then maybe in the next run, it will choose another one, right? And in this sense, we can change the XT to ZT, right? Okay, so the performance matrix here is to minimize the regret, which is the difference between what you actually accumulate during this process, total reward, compared to the optimal one, right? We want to minimize the difference. And the learning agent has to balance this kind of exploitation and exploration. And the XT can be replaced by ZT, which is the LTC and the CTL view of this kind of data, right? So basically, privatized and corrupted version of the feedback.
Question.
Oh, sure.
If it's a corrupted version, then DT does not represent the true reward of the user anymore.
But this corruption still has some probability to be sampled from the true user.
Very, it's true, but usually like XT without corruption represents the reward the user receives, right?
Yeah, yes.
But here DT is not that reward.
Yeah, but you can get one like this way, right? The base similar like this. If the reward is greater than one, the base strategy for the adversary still keep the bad distribution as a bad rate distribution. It's still greater than one. but with a different mean, because if the reward change to some other scalar, then the neural can figure it out. You can figure it out.
Okay.
Yeah. So that's a subtlety here, right? You can figure it out. Okay. Okay. So another application of this kind of LTCCT we can apply to large language model alignment. So this alignment process is basically a post training process. Try to make sure that the pre-trained model is further trained to align the human preference. It is basically a common step in all these kind of large language models. No matter whether you, there are two commonly used paradigms for large language model alignment. One is RL based on the left-hand side. One is RL free, which is basically use a supervised learning approach to do the alignment. But for both methods, we will start with so-called preference data, which has a bunch of questions, and for each question you have, say, 2 answers and some preference, which says that which one is preferred by the humans. Okay, the goal here basically want to minimize the suboptimal gap. You want to find a policy per head such that the utility between your policy per head and the optimal or maybe some other comparative policy is close, right? You want to minimize the gap. And you can actually think about like, the preference data can be cropped, and also the preference data is often sensitive, right? If you are using ChatGPT every day, you are often given, once in a while maybe, I will often given 2 answers, right? For some questions, suddenly if you ask you to rate which one you like, right? So I believe you came across that situations, right? When you interact with ChatGPT, if you ask you to rate the answer, okay? For some reason, I always give the wrong answer, actually. So I just want to do some trick on this. Okay. Okay. So this actually gives us an outline of a talk. For mean estimation, we will talk about our performance metric, which is a high probability error rate. And I will try to give you the intuitions between the separation between the separation results between LTC and CT, why the order matters. And I will briefly talk about the online multi-bandits because it's a direct application. But I do want to mention that as a byproduct of our result, we actually identify a bug in the existing result, which shows that their upper bound is actually not correct. Finally, I will talk about the large language alignment, about the algorithms and the main results. The key takeaway message from this talk is very simple. The privacy protection and the corruption, the order of them matters. Okay, so let's talk about the mean estimation part. We first define the performance matrix. We take the minimax perspective, which is the worst case guarantee. And in the typical case, we were dealing with something like this, right? So the expected version, we want to minimize or we want to bound the distance in expectation between your estimator and the true mean. Since we are considering the minimax framework, we have to take the influence over what we can control, right? This is what we can control because we can design the estimator. What we cannot control is that the adversary, the adversary can select the candidate, the hard instance in a class. So we define this minimax value as this, minimax error. And this script P basically is a class of distributions you are interested in. For example, all the distribution with bounded second moment. In this talk, we only focus on bounded distributions. Okay, so naturally we can adjust our previous definition to the LTC CTL setting. The only change here is very simple, right? We just replace the x1 to n by z1 to n. That's it. So of course, we have more to control here. We can control the privatizer, right? That is what we can design. We can also design our own estimator, but we cannot control the distribution, and we cannot control the corruption, right? And we take the inferior and supreme over all these quantities. If the z1 to n is coming from LTC, then we have the LTC quantity. Otherwise, we have the CTL quantity. Right? Okay, so this is very standard minimax framework, but this is not sufficient for our case because we are interested in high probability version. Why? because in downstream application of mean estimation is especially in reinforcement bias, we are more interested in the high probability version. Okay, so we are trying to design the high probability minimax error rate. So for high probability, we are interested in something like this, right? With small probability, the difference between your estimator and the true mean is larger than this threshold, right? So basically, this event happens with a small probability. And we take the inferior and superior as before. Of course, we want to minimize this threshold, right? So we take the inferior again, and we define this one as the high probability error rate. Intuitively speaking, this is very simple. It just says something like this. This quantity is the minimal error rate that any LDP estimator can achieve with high probability for all distribution and for all Hoover corruption model.
So you know alpha,
We know alpha.
so shouldn't that be a parameter?
Yes, I think this, yeah, we ignore that in this one, but we should. Yeah. Yeah, but I think in our algorithm, we do not utilize alpha. Yeah, if I remember correctly. Okay, so yeah, let's do a warm-up quiz. Okay. So okay, so let's have a guess. So LTC, CTL, which one do you think has a larger error? So privatizer before the corruption or privatizer after the corruption? So maybe this is so complicated, right? I will give you a hint. Let's consider Borel distributions, right? The P is just a Borel distribution. And the privatizer is just a randomized response, random flipping, we just introduced. And the corruption is just also 0 to 1 corruption. So basically the binary distribution is also just binary, 0 and 1. Notice that the adversary distribution is definitely not, the adversary corruption is not random flipping. Otherwise, there's definitely no difference, right? So, I can give you another hint, maybe. You can even consider the inner distribution to be a Borel of 0, basically, which means that all the input density is all zero. What does it mean? It means that if it goes to LTC and CTL, you just count how many ones in the end. If there are more ones in one situation, then that is situation where has a larger error, right? Okay, what's your guess? Of course, we can pass the last option, right? They are definitely not the same. If you are not getting lost in the first maybe 20 minutes. Yeah.
You show the rate on the previous slide.
Okay, so I think you do not have to worry about this definition of this one because this is just for technical side, right? I mean, the main purpose of this quiz is just to build your first principle intuition, like
LTC.
yeah. Cool. So why? Can you give?
I can flip all 0 to 1.
So yes, so the CTL has some goodness actually. The CTL, because you can smell like this. Where this is the first principle intuition. I will give you 2 more intuitions. The corruption in this case, the base corruption in this case, just put whatever to be 1, right? And for CTL, if you flip alpha almost nearly alpha fraction of 0 to 1, the LTC can flip back. But you mean the CTL, right? The CTL case, the privatizing after the corruption, the random flipping of the privatizer can flip back. But for LTC, it cannot. That's it. Okay. Okay, cool. So this is one way out. You have a 1 over epsilon factor difference between LTC and CTL. That's the first difference between the rate. A lot of difference compared to our non-private one is that the second term will have this 1 over epsilon term. That is a privacy cost because we have to protect the privacy. Then we have to suffer this kind of 1 over epsilon multiplicative factor compared to the non-private one, right? And again, if we have alpha larger than 0, we have the corruption. Then LTC has a larger error rate due to this kind of separation. Okay, so I briefly talk about the relation to existing works. There are some works on this setting, CTO-ANTC. Of course, they do not call the setting as CTO-ANTC, but they are mainly focusing on the MLC expected version or the constant probability. That is not sufficient for a downstream task. And another thing I want to highlight here is that if you look at the first term, you can see that in the LDC, the privacy and corruption parameters are coupled together, right? But in the CTL case, they're just additive, right? The corruption is the first term and privacy is the second term. There is no coupling. They are separate. Okay. So we need to prove this kind of min-max rate, which is a big theta. So we have to show a big omega and a big O, right? For the big omega, which is a lower bound, this is standard lower bound statement. It says that no matter which parameter you choose, which estimator you design, there always exists some kind of biodistribution and a biodistribution mechanism. You have to suffer this kind of mean estimation error. And the proof idea is quite, I think, is simple. We divide into two parts. We first only consider the privacy without any corruption, and then we consider corruption. So for the first part, we only consider privacy. That's definitely a widely low bound, right? Because if you consider corruption, add on it, if you only make the problem even harder. So for the privacy term, which is the second term, we will show that using this kind of standard LLM's 2-point lemma and some kind of coupling and some kind of inequality. And for the second part, we will use some classical property of Hoover corruption, which is also very basic, actually. So I think the proof is somehow interesting. I will go over it. I promise this is the only proof I will show in this talk. So for the privacy alone part, we only have X and a parameter, which is epsilon local differential value. And we obtain the Y, right? So we want to show that we have to suffer the second term. This is very standard, I think. Okay, in order to use the LLM's 2-point lemma, we have to choose 2 points, right? Which is hypothesis testing. You choose P and P prime, 2 points. And the mean difference and the TV distance are both within the on the order of gamma, right? Okay. And we define the M and M prime as a marginal distribution of P and P prime after this LDP channel. So because the data will pass through this LDP channel, this privatizer. And we define basically the Y subscript N and Y prime subscript as the ID samples from M and M prime. Okay, so here's our goal. If we can show this event, then we are done, right? So the 2 sequences are equal with probably at least 2 delta. Then we cannot distinguish them, so we have to suffer the mean estimation error of big O of gamma. Okay, we have to show such kind of probability. So how can we show this, right? How can we show that the Y, if the Y and Y prime are equal, this is a sequence of ID samples from this, from this M and ID samples from M prime, they are equal with probably at least 2 delta. So the first thing we can show is that, they are equal is equal to Y minus if they are not equal, right? And the probability for 2 random variables, they are not equal is actually equal to the TV distance, right? This is basically by standard maximal coupling, or basically, if you want to define TV distance, you can define something like this. You use the maximal coupling. Okay, now it suffices for us to find the upper bound on the TV distance, right? So how can we find the bound on upper bound on TV distance? For a product distribution, I think you must think about Pinskers inequality, right? So let's convert the TV distance to KL, because KL have the chain rule, right? That's the reason why we want to work with chain rule, or we work on with KL. So, but instead of using Pinskers inequality, we will use the so-called BH inequality. And then the only step we have to deal with is to find a bound on this kind of private KL divergence, and we can use some existing result. And because of the choice of this P and P prime, we have this kind of final bound. And in the end, we just choose the parameter gamma to make sure that the second term is on the order of 2 delta, then we're done, right? So that's it. We finished the first part. Very simple, right? So you may wonder why we have to use pH inequality in the first step. Because if you use p-square inequality, there is no exponential term. Because there is no exponential term, it will not give you the high probability bound. So basically, p-square inequality is quite loose in certain sense, right? Right. So I mean, for standard expected version minimax framework, p-square inequality is enough. But for high probability version, you really have to use pH inequality. That's a main point. Okay. So now let's go to the second part. So we have put the first part, which gave us the second term in the theorem, right? Now we are interested in the first term. So why there is a separation? I think this is the most interesting part, right? Why in the LTC we will have this 1 over epsilon factor? So we will utilize this folklore fact. Very simple. It says that if you have two good distributions, they are TV distance close on the order of alpha, then after the corruption of Hooper corruption, you cannot distinguish them. Think intuitively also very simple, right? Just because you can find a middle point such that after you can spell like this, right? I have a G1 and a G2, both of them will pass this kind of corruption channel. You can always find a middle point that they are equal. So this is basically the geometric understanding of this lemma. Okay. So how can we utilize this lemma in the proof of our setting? Let's consider the LTC. Okay. So the first observation we should note here is that as long as we can show the y and y prime for 2 points, like your P and P prime, right? Y and Y prime are close in the TV distance on the order of alpha by the fact above, then we cannot distinguish the true inner distribution X prime or P and P prime, right? We cannot distinguish by the fact. Okay, so another property we should use is, I think this is also a very basic property in information theory, which says that the LDP channel is actually a contraction mapping in terms of TV distance. That's it. So after your data pass through a LDP channel, your TV distance will be contracted by this kind of epsilon factor. So what does this mean? It means that you can enlarge your X and X prime TV distance by a factor of 1 over epsilon. You are safe because this by the contraction of LDP, your distance between Y and Y prime is still on the order of alpha. So that's the reason why in the LTC, you have a larger estimation error. Because you can choose a larger, choose 2 points which has a larger distance. Right? Okay, so you may wonder why we cannot apply the same kind of reasoning to the CTL case. In fact, we cannot because this is somehow tricky. Like for the first term in the CTL case, what we can show for the lower bound is only something like this. It's just we ignore the privatizer, and because Y and Z are equal, then there is no contraction, and then we only need to, or we have to guarantee the X and X prime on the TV distance of alpha. So this is what we can show for the lower bound. So you will wonder, okay, maybe your lower bound is not tight, right? Because you can only show this lower bound on the order of alpha. Maybe in reality, the actual estimation error is larger than alpha, right? But this is just a lower bound. This is what we can show. But in terms of that, we have a matching upper bound, so it's fine, right? So that shows something like something interesting, right? For low bound, you can only show something like this, but as long as you have an upper bound, you are safe. So now let's turn to the upper bound. for upper bound, we have to design an algorithm to match this lower bound, right? Once we can design an algorithm to match our previous lower bound, we are done. So the algorithm has two parts. One is a privatizer and one is analyzer. Right? This is what we can control, what we can design. And since we consider boundary or bounded distributions, we consider bounded distribution not necessarily boundary. The first thing we have to do is basically we will convert it to boundary data. So suppose our xi is between -1 and 1. It could be real data, and we will use this so-called random rounding to convert to this kind of boundary data, 1 and -1. And then we just apply randomized responding or randomized response to give this privacy guarantee. Okay. And for the analyzer, it's quite simple. We just take the empirical B. That's it. So, okay. Here's the tricky part. So why can we still assume that the bounded value on this option? I think later was asked this question, right? So, for example, for the CTO case, the privatizer's input is something that has already been corrupted, right? And we assume that the corruption can be done in arbitrary way. The adversary could choose arbitrary corruption by distributions, right? But the analyzer or the privatizer can easily figure out if it is not bounded because we know that the true distribution is bounded, right? So the base strategy for the adversary just still stick to this kind of bounded case, right? To have the base damage to the corruption or to the estimation. Okay. So this is the upper bound. Sure.
What knowledge actually the privatizer, the analyzer has about the corruption? And the true mean, like they're bounded, so they may have to know what the bounded.
Oh yeah,
them,
yeah,
right?
yes.
So what other information?
No,
they need to know.
No, just bounded. Yeah.
And they don't need to know like what kind of corruption strategy.
No. Otherwise, it's not interesting. Yes.
Oh, alpha.
Oh, alpha. If I remember correctly, in this sense, I think they do not have to lead to low alpha, but I think in the online banded case, they lead to low alpha. But I think in the mean estimation, they do not lead to low alpha. Yeah.
I guess the bounds are common knowledge.
Yeah.
What happens if alpha equals to 0, 1, like extreme case, you don't take the true distribution at all?
Oh, we assume the alpha between 0 and 1/2.
Oh.
There is a breakdown point.
Can you say something about why this wouldn't work for a strong adversary with a strong contamination model?
Oh, it will work. But we only consider Kruger corruption for the sake of simplicity, and also because we want to deal with online multi-bandits, we want to get rid of some kind of dependency issue in this downstream task. So we focus on Huber corruption. This will work for strong content.
And what about the heavy tail?
Yeah, we will. Yeah, I will show you later. Yeah, cool. Okay, so this is upper bound. So basically, for n large enough, we have the same estimation error as a lower bound. So you can see there is a burning period that for n larger than some threshold. I think this is the common issues in the Huber corruption model, but for strong contamination model, there is no such burning period. I think another important, interesting fact I want to mention here is that if you are familiar with differential privacy, right, there is another mechanism for privacy, which is Laplace mechanism. You just add some Laplace laws into your data. But it turns out that if you have corruption, then you add this Laplace laws, which is unbounded, will make you analyze design of the estimator much more difficult. Actually, if you use naive approach to design your estimator, it's not possible for you to have the optimal rate. Okay, so this is for heavy tail case. That if you consider this particular case heavy tail distribution, which means that the case moment is bounded, then you just add this kind of 1 minus 1 over k term on the power. Okay, this is also optimal. We have lower bound and upper bound. In this case, your estimate leads to do truncation. Okay.
Yeah, that makes sense.
Yeah. Yeah.
Do you need to know the gate?
Yeah. Okay. So I will briefly talk about this the online MAB. So it's quite simple, right? So I think I should not introduce the UCB algorithm, right? So it's an upper confidence bound, and for each round T, we compute this UCB index, which is summation of two terms. One is the mean estimation term, and one is some kind of boundless term, right? To encourage exploration. So this term is basically one is for exploitation, one is for exploration, and basically it tells us that we should be optimistic in the face of uncertainty if you have online samples, right? So the key question here is how to design this kind of boundless term or the confidence interval, right? So to this end, we have to utilize our previous upper bound of the mean estimation, and we just converted that kind of estimation error into this boundless, then we are done. And you do some math, you have this upper bound, and I will skip this one. For lower bound, you have a really matching up a lower bound up to log factor. And I would like to highlight that because of our lower bound, we actually identify a bug or an error in the SOTA result for private heavy tail bandits because our lower bound is actually larger than their upper bound. So basically, their upper bound is not correct. Yeah. Okay, interesting. Finally, I will talk about, you can refer to the paper for more details. Okay, so sorry, I forget about this. For the, maybe I should not go over this one, maybe.
Just a multi-and bandit setting, the corruption is not to be, procedural corruption is specified along your learning online path, or is it done once?
It's a good question. So it's still Hoover corruption. So it does not see the sample. It still just chooses this kind of distribution. Yeah. Yeah, because there's some kind of very tricky dependency issue of this kind of, if you consider strong contamination, like which assumes accuracy low everything, then it's kind of, so we try to avoid that kind of issues in this paper. Yeah. But I do think that is an interesting problem. Okay. For alignment, let's first introduce the setting, right? So you have an offline preference data set, and XI is a prompt question, and A0 and A1 are two response from some reference policy or base policy or SFT policy. And you have the preference label, which is sample from this kind of border distributions. And this probability is characterized by this BT model. And this BT model is given by the sigmoid function with respect to a true reward function, the R star. And our goal is here is to minimize the suboptimal gap between your policy and the optimal policy in terms of this kind of expected reward. Okay. So this is basically offline, like maybe offline reinforcement problem with preference data. So in this talk, I will mainly focus on the supervised learning approach, which is the DPO, maybe one of the most popular methods for alignment. So what is the algorithm? The algorithm,
And what does the notation represent? Top line, XI?
Oh, the XI here basically means that the XI is part of the equation, right? The equation is sampled from some underlying distributions. And the AI zero is one answer for that equation, which is sampled from some reference or base policy. That's about the naive GPT2 policy, like just after the pre-training or after the supervised activity. Okay. And the AI1 is another response. And the YI basically say which one you are preferring, 0 or 1. If it's YI equal to 0, then which means that the human prefers the first action or first.
They're sampled from the same distribution, A0.
Oh yes, A0 and A1.
So the probability is we won't have.
The probability is
That AI one is greater than AI zero.
no, because that is just two responses, but how which one is preferred by the human is determined by this. The probability is determined by this sigmoid function. It's not maximum no one. So basically, something like if the A1 has larger reward under this true R star function, then it has a high probability to be preferred by the human.
Oh, that's not a greater than, that's that greater than. Look.
Oh, that is basically preferred by.
Prefer.
Yeah,
Okay, so these are,
yeah, it's not greater than.
these are not real numbers.
Yeah. Yeah, sorry for the confusion. Okay, so this is setup, right? This is a standard alignment setup, offline alignment setup.
Also here, the A0 and A1 are given, right? It's conditional on that too. It's not a random variable.
Oh, yeah. Yeah, yeah, the condition is excited. Yeah, yes. Okay, so let's focus on the supervised learning approach to this alignment. This is very simple, actually. It's just a supervised learning. You minimize some loss. That's it. So the loss is just log loss. And the probability inside the log loss is some kind of difference. Okay, so if you're confused about the location, it's fine. I think that's not a main focus on this one. Because just about like this is just log loss over the policy pi. And we want to find the base policy which minimizes this loss. And how we come up with this loss, basically from the k-regularized objective, right? We do some kind of reparametrization of this reward using policy, that's it. But again, that's not the focus of this talk. Okay, so this is just a supervised learning problem. You can symbolize the greedy version or greedy algorithm. You just want to be greedy with respect to the data set and to minimize the loss, right? For any greedy policy, you should think about like there may be some kind of overfitting or over-optimization issue, right? Since if your data set, if your offline data set does not cover some region that where, then if you do optimization over that region, you will have this kind of over-optimization issue, right? You think you are doing good, but it turns out it is not, right? So how can we have some kind of formal uncertainty guarantee, right? Or uncertainty quantification in your algorithm design? That is the key, right? And in the online setting, we will introduce some kind of bias to be optimistic. But in the offline setting, we will do the opposite one. We want to be pessimistic, right? Okay, how can we do pessimistic update? In the tabular linear case, you can minus some bias. That's very easy to do. But since we are considering general function approximations, we do not assume any, the R star could be any function. Okay. So in this case, how can you design your bias and how can you introduce this kind of pessimistic behavior? That is a key question. Fortunately, it is solved by some people. A very recent paper. It says that, okay, if you have just one line change compared to DPO, you can have a very good performance guarantee. You can see you just replace the H DPO function by this phi, and the phi is just has an additional linear term compared to the previous H DPO. That's it. Just one line change. And what's the benefit of this kind of change? In DPO, the base performance guarantee you can obtain should depend on how well your preference data cover all the possible policies in your policy class. So you have to make sure that your offline data set has a very good coverage over all the policies. That is called all policy contextuality in offline IM literature. But if you use TypeShield, your performance guarantee will only scale with the so-called single policy contextuality, which means that it only requires your offline data set to cover the comparative policy you are competing with. Right? Single and all. The single one is much smaller than the all policy contributor. So you have a tighter upper bound. And the algorithm is very simple, just one line change. But the fundamental idea is very simple. It just, as I told to later, it's just Cauchy swath plus change of measure. So we can easily consider privacy and corruption in the large language model, as I mentioned before, right? You can apply the LTC CTL to the labels, right? You can change the label from Y to Z, right? And you can also consider even strong privacy guarantee here, which is central differential privacy, which means that you are given two data sets D and D prime that only differs by one sample, Y2, and you require that the output of policy you obtain after the alignment should be similar, right? So this is the typical standard DP guarantee applies to this kind of preference data set. Yeah. So what it would be our algorithm? Our algorithm, another one-line change from the non-private capsule to private capsule, we call square capsule. Why we call it square capsule? Because we change the log loss to square loss. That's it. Okay, so we just change to square loss, one-line change. Okay, so why we have to change to square loss? Because the square loss is bounded. Log loss is not bounded. The bounded is helpful for us to deal with corruption, right? And that's it. And this intuition actually comes from a mean estimation. If you remember that in our mean estimation, we also have this kind of ratio C epsilon in front of our samples to debias it, right? So we have the same behavior here. If you want to know the fundamental reason, it's also very simple because if you are doing theory, log loss, square loss, both have this kind of uniform convergence error rate, right? They are the same, 1 over n. So it's not a big surprise that we can have the same result. Okay. Okay, so that's a local model. And if we want to study the privacy in the central model, another one-line change. So instead of doing this greedy policy, we will do soft max. The soft max in privacy is called exponential mechanism. You just sample from this kind of distribution. And the weight for each policy is proportional to this loss. Okay. Of course, I would admit that this central square capsule is not computation efficient because we basically assume a finite function class of policy class. It's more from a statistical perspective. It's not from a computation perspective. Yeah. So the final theoretical guarantee, something like this. For the local model, we can show that the suborbital gap is on this order. So the kappa pi star is some term related to this coverage. It's some coverage. But you can see that for LTC, the gamma term has an additional C epsilon factor, which is on order 1 over epsilon or epsilon smaller than 1, right? So you have this kind of additional factor in LTC. And for central model, you have a better privacy cost because the central model is somehow weaker than the local model, right? You have a 1 over root epsilon rather than 1 over epsilon in the central model. Okay. So I think the key contribution in this work is something we derived the generation error bound for this square on the privacy and corruption. I think this is somehow very useful because if you are doing theoretical reinforcement theory, this kind of generation error bound is used everywhere. So in principle, you can apply it to everywhere. Okay. Okay, so there's some kind of nice extension we have done. So in our current model, we assume that this kind of probability A1 is preferred over A0 is characterized by some kind of underlying true reward function, but that it may not necessarily be true, right? Because if your preference probability is characterized by some underlying reward function, it implies that if A is preferred over B, B is preferred over C, then A is definitely preferred over C. That is not the case. That is not always the case in practice, right? So if we want to model this kind of general preference matrix, then we have to consider general preference model, get rid of the BT model. Yes, we can do that. And it turns out that this is another benefit of using square loss. Okay, so let's get back to that student's question, maybe. So, what if we consider strong adaptive, contamination or corruption? The algorithm can even first see the samples, and then try to say, okay, I will corrupt at the most alpha fraction of the samples. So, in this sense, this is a stronger one, right? For this kind of alignment problem, we can still give this kind of formal privacy and utility guarantee on the privacy and the corruption. But currently, it only works for the linear function approximation case. Like the reward function is a linear function. It's not a surprise because if you consider linear function, basically the alignment problem, I would argue, reduced to a logistic regression parameter estimation. As long as you have this kind of confidence interval, then you can do offline alignment, right, with some kind of pessimistic term, and to do this kind of uncertainty quantization. So that's the reason why, for the linear function approximation case, we can do both RLHF and DPO, and give a unified analysis by reduction to logistic regression. Okay, so yeah, I think if you are interested in this line of work, you can refer to our two papers, this year's SML. And we also have done some kind of small scale experiments to verify this kind of effectiveness of our algorithm. Okay, but the key takeaway message for this talk is that the order of local differential privacy and the corruption really matters. I think we still have 3 minutes. One last thing. Okay, so after I joined Winston, I have been working on this kind of private reinforced learning and bandits. So my collaborators and I have been working on across different problems, from multi-bandits to contextual bandits and reinforced learning, and recently about the large language model alignment. So if you are interested in this alignment work, you can check out my recent Sigmatrix tutorials on private IR. Okay, thank you.
Questions?
It was a little surprising that the analysis algorithm and problem was just the same one, as opposed to some kind of robust estimate.
Yeah, sure.
Do you have any thoughts on that?
Because if we consider this kind of bounded case, it's natural, right? Because if you bound it between 0 and 1, basically that constant is ignored in the bound, right? Because if your input distribution is heavy tail, then you have to do truncation, right? That is somehow like a robust estimate. If your input distribution is just between 0 and 1, then there is no need for you to do any robust estimate. But if your input distribution is heavy tail, you need to do some kind of robust estimate, which is truncation. Truncation itself is a robust estimate, right? Okay, a lot of subtlety, because we only consider one dimension case. If you consider high dimension mean estimation for vector, that's a totally different story, because even for Gaussian mean estimation of high dimension case, only I think 2016, only until 2016, there is a first paper which gives a computation efficient mean estimation on the corruption. So if you care about this kind of, if you do not care about the computation efficiency, you can use this so-called two-key median, right? That will give you this kind of, that is the one particular mean estimation, a robust estimator for high dimension vector without computation, constraint. But if you want to give a computation efficient estimator for high dimension distribution, then you have to use the recent advance in robust statistics, which is a filtering algorithm. And I think that the key reason why we can use this naive or very simple estimator is because we just deal with one dimension.
What assumptions are you making about the contamination?
The contamination, basically, in the majority of the talk, we focus on the Huber corruption, which means that
you're contaminating the target distribution with some other
Yes.
What are you assuming about that?
Low assumption.
So essentially, you can throw out the alpha fraction of the bad ones, right? So very large ones, just throw them out and then you work it.
Yeah, because you can something like this, right? So, because this, if you consider boundary distribution, then this impact of this kind of alpha, yeah.
Bounded also.
For unbounded, yeah, we can throw out.
So I mean, essentially, we throw out an alpha fraction of really high ones on either side, then you'll be fine.
Oh yeah, that is called a trunk. Yeah, exactly. Yeah,
That'll
exactly.
work more
Yeah.
data, yeah.
The estimate you mentioned is called trimmed mean. Alpha on both sides. Yes.
That would work fairly well on this.
Yeah.
Any other questions? Now let's thank Sunil. He's not very far away, maybe 40 minutes.